Hi there, I'm Justin Pritchard, and in this video I want to crunch some numbers on a popular saying amongst car enthusiasts that you're probably familiar with. This car has so much torque, it doesn't drive down the road, it actually spins the earth underneath it. Now obviously that is a massive exaggeration, but it got me thinking, how much torque would you actually need to spin something as big and heavy as our planet? Set on figuring it out, I started by making some coffee. Then I sat at my computer and opened the calculator. Then I took Ghost for a hike to clear the smoke from my brains. Then I realized I needed some help, so I got a hold of Mr. Boucher.
Hi, I'm Rob Boucher. I'm a teacher here at Bishop Alexander Carter Catholic Secondary School. I'm the program leader for computer studies, sciences and technological studies, and my courses namely are related to physics and mathematics.
Mr. Boucher was actually my physics teacher way back in high school, and I remember his class well because he was a car guy just like me. In fact, here's an old picture. A photograph on paper? God, I'm old. Look at my stupid hair. Here's an old picture of us checking out his Acura 1.6 EL. Anyways, I asked Rob, who says I can call him Rob now, to help me figure out which calculations I would need to do, and then I spent about 2 weeks playing around with them on my own, and then we went over them together with Rob double-checking and providing advice and helping clean up my initial work. I won't explain all the number crunching that he's doing in full, as that would take a while, but here's a fun montage for illustrative purposes. Right now, Rob is determining the amount of torque required to rotate a sphere equal in size and mass to our planet. Specifically, that's a sphere with about a 6,400 kilometer radius that weighs about 6 septillion kilograms. Now you need rotations and time to figure this out too, so we're calculating the torque required to rotate that big ol' sucker from 0 rotations per day to the Earth's current rotation of 1 rotation per day, and making that happen in a time of 1 second. I'll let the physics expert explain the gist of it.
You have to start at the end and work your way back. So big picture, the torque required to start rotating the Earth from a standstill to its current rate of rotation is a change in angular momentum over a period of time.
And here's Rob explaining why we're calculating torque and not something else like force.
So with torque, I'm applying a force downward on this door handle. However, it results in a displacement that's rotational. It's not unidirectional, as is the case with work. So essentially, work is an applied force resulting in displacement in one axis, whereas torque is an applied force resulting in displacement in a rotation.
So a few final calculations and we have arrived at the figure. In order to get a sphere the size and mass of our Earth to spin from 0 revolutions per day to 1 revolution per day in a time of 1 second, you would need 5.2 decillion foot-pounds of torque. That number is 34 digits long and is equal to the combined output of about this many of these Porsche Panamera Turbo E hybrids, which have 626 foot-pounds of torque each, but that would cost something like $17 sextillion, which looks like this. Or if you like, that's about the combined torque output of 1 quintillion top-fuel dragsters for every living person on Earth. So unsurprisingly, no car on Earth, or even every car on Earth, can actually make the planet spin beneath it. It's literally 5.2 decillion foot-pounds of exaggeration. I'm Justin Pritchard.